Hello everyone. I'm Saptarshi Mukherjee. I'm currently working as a software engineer 3 at Google, and I've been in computer programming for a good amount of time now. I've been to the ACM-ICPC Regionals, and you can see some of the titles that I've acquired in Facebook or Meta Hacker Cup, a master at Codeforces, 6-star at Codechef, and yeah, I've graduated in BTech honors in CSE at IIT Bhilai, and I've been in some research work as well in blockchain, edge computing, and advanced graph algorithms. So, yeah, in this particular series of videos, I'm going to cover dynamic programming, a very important concept for both competitive programming as well as your hiring exercises. And in this series of videos, I'll be focusing on CSES problem set. It's a great problem set for beginners, for intermediate coders. You cover all the essential aspects of a topic from these problem sets. So this was one of the things that I actually covered during my preparation, and there were other things I covered. I think this is a good thing to actually cover end to end. Then you get, 90% of all problem sets. Then you can proceed towards harder problem sets. So I'll be doing the same thing. In these videos, I'll be covering these basic problems. I'll tell you how to apply dynamic programming, how to think in terms of dynamic programming, and also other algorithms that will come later. And then after we are done with this, I'll basically try to extend it to harder problems that are outside this website, maybe in other websites. We'll pick up some really hard problems and I'll show you how using these problems we can solve those problems. So yeah, stay tuned and see how we are solving these problems. In this session, I'll be covering dice combinations, and this is the first session of dynamic programming, so I'll be going through the basic dynamic programming approach, and then I'll come to how it works in this problem. So yeah, let's get started. The question is dice combinations, which asks count the number of ways to construct sum n by throwing a dice one or more times. Each throw gives 1 to 6. So if n equal to 3, then these are the 4 ways. So if n is equal to 3, we are basically saying it can come from ones 3 times 1, it can come from 1 plus 2, it can come from 2 plus 1, it can come from only 3. Only 3 means one time dice fell, it gave a 3. 1 plus 2 means first time 1 came, the next time 2 came. 2 plus 1 means first time 2 came, next time 1 came. So these are all distinct ways. Now, how to solve this kind of problems? For higher values of n, similarly, you can have all sorts of distributions. So it basically asks you, hey, in how many ways can you give me some integers whose sum is equal to that n? Now, the ordering can be anything, bigger numbers can come later, can come before. But if I see step by step, the first thing that strikes to me is, okay, the first step can be anything. The first step can be 1, can be 2, or can be 3. N equal to 3 means that the first step can be 1, 2, or 3. If n was bigger, it could have been 4, 5, or 6 as well. Now what I see is, okay, if the first step is equal to 1, then these are my 2 ways. In this case, the first move is equal to 1. If first move is equal to 2, then this is the only way available to me. After 2, 1 will come. Then my sum is equal to 3. So first, if 2 comes, then this is the only way. And first, if 3 comes, after that nothing needs to come. So that will have one way. So only 3 comes, after that nothing needs to come. So yes, 3 itself is another way. So what do we get from here? Somewhere the first one helps us segregate that, okay, the first one can be anything. Then comes the next level. That, okay, if the first one is, let's say, 1, then the next one can be either 1 or 2. So somewhere, if we see level by level, that might be interesting. So let us look at that maybe for a slightly bigger example. Let's say n equal to 4. For n equal to 4, I'll do the same thing. I'll say, okay, the first step can be anything. It can be 1, 2, 3, 4. It cannot be 5 or 6. So I'll not write 5 or 6. I will write 1, 2, 3, and 4. This is the first step. The first time the dice falls, these are the 4 possibilities which are valid. Now, when 1 comes, what remains from 4 is basically 3. When 2 comes, what remains from 4 is 2. When 3 comes, out of 4 only 1 remains. When 4 comes, out of 4 only 0 remains. So now these are the remaining things which now I have to solve for. So let's continue doing the same thing. When I'm at 3, when 3 is remaining, then again I have 3 options. Then I again have 3 options. I can have 1, 2 or 3. The next dice can have 1, 2 or 3. Each will give me some possibilities. So let me complete them. If 1 comes, then 2 are remaining. If 2 comes, then 1 is remaining. If 3 comes, then 0 is remaining. Okay. If 2 is remaining, I can say, okay, we have 2 possibilities now. Directly 2 can come or only 1 can come. If 1 comes, then 1 is remaining. If 2 comes, then 0 is remaining. Out of 1, when 1 is only available, you have no other way. Only 1 can come and then you will stay back with 0, which means no other steps needed. And if 0 is there, then fine. No other step needed. Over here, when 1 is there, you have only one way. That is, throw a dice, it should have a 1, and then you will get completion. 0 means completion. Let us complete the right parts as well. If 2 would have come over here, same way, we would see 1 or 2 are possible. So 1, 0. Here 1 is possible, so 0. Similarly over here 1 is possible, so it is 0. And we are done. Now the thing is, what do you see over here? This is one way. 1, 1, 1, 1. This is one way. Out of all possible ways, this is one way. 1, 1, 1, 1. Similarly, I can say 1, 2, 1. This is another way to get 4. To get a sum of 4, this is another way. Similarly, I can say 1, 1, 2. This is another way. So, every leaf of this tree or every last level kind of node of this tree, or I can say every terminal node of this tree, provides me one way. Each terminal node tells me, okay, from the top up to myself is a way. Each terminal node tells me. For example, this terminal node tells me that from the top follow up to me, I will give you one way, 1 to 1. Similarly, this tells me you follow from the top up to here, you will get 3, 1. So this is another way. Similarly, you can get 4 as well. So each line that comes up to the bottom, each such line is basically one way. So in this way, we have a total of 8 ways, right? So you can keep on doing it and you can say, okay, how many times I'm reaching 0? That kind of a thing. You can keep on doing that thing and you will get the answer from there. Now, from this structure, that is a recursive technique that, okay, you keep on calling things and gradually will get the answer. There is another aspect to it, which is from here 1, 2, 3, 4, 5, 6, 7, 8. We have got answer equals to 8. Another thing we can say that for this 4, for 4, this is one option, this is another option, this is another option, this is another option. 1, 2, 3, 4 are the first moves options. So if I choose the option 1, then I remain with 3. For 3, how many ways are possible? So let's say I assume that the first move is 3. Then how many ways are possible? If you see, there are 1, 2, 3, 4. 4 ways possible. There is branching, you are getting 4 different ways. So basically this part provides you 4. Similarly, if you would have come through 2, for n equals to 2, when 2 are remaining, for those 2, how many ways are possible? You have only 2 ways possible. In this part, how many ways are possible? Basically, when this 1 is remaining, only a single way is possible. And for 0, how many ways are possible? This is itself a way. 0, if 0 has come, this is itself a way. Within this, multiple ways are not possible, but 0 itself is one way. Right. So if we take 4, that means I will stay back with 0, that is one valid way. So I will count this as 1. Now, what does this mean? This means if my first move is 1, then I have 4 ways. If my first move is 2, I have 2 ways. If my first move is 3, I have 1 way. If my first move is 4, I have 1 way. So somewhere, if I find these individual ways, then the summation of these gives me the value 8. Which means somewhere, these smaller parts, if I just look at this much part, which is basically telling me that 3 can be brought in how many ways? 3 can be brought in 4 ways. 2 can be brought in 2 ways. 1 can be brought in 1 way. 0 can be brought in 1 way. If I know the values of these smaller numbers, smaller sums, 3, 2, 1, 0, from there I can get the answer for n equal to 4. So I can basically say that the answer for 4 can be obtained if I know the summation of the answers for each of these, 3, 2, 1, 0. If I know the answer for 3, you see we are doing the same thing down the line. We are basically asking that for 3, how many ways are possible? For 2, how many ways are possible? So if I say, okay, for those values that you find for 3, 2, 1, and 0, then simple addition will give you the total number of ways in which 4 can be obtained. That's it. And now, if you add them up, you will get 4 plus 2 plus 1 plus 1 is equal to 8. This, my dear friends, is basically known as the optimal substructure. This is the optimal substructure which says that if you know the answers to the subproblems for 3, for 2, for 1, for 0, if you know the answers to the subproblems, you can get the bigger answer. You can get the bigger answer for n equal to 4. So if you know the answer for smaller values of n, you can get the answer for bigger values by simple addition or something like that. So that is known as optimal substructure. Now the thing is, still we have to do a lot of things. We have to go down to 3, 3 also we need to find, 2 also we need to find, 1 also we need to find. Here we will make an observation. For this 2, look over here, for this 2, in order to find out how many ways this 2 can be brought as a sum, we have to focus on this particular subtree, you can say. So this particular computation needs to be done. If you look over here, we are doing the same computation over here. This part and this part are exactly the same thing. For 2, we have done the same computation twice. For 1 also, if you see, for this 1, we are doing the same computation 1, 0 so many times. 1, 0, so many places we are doing it. So, the larger it grows, you will find these redundancies. The thing is, this 2, if it has 2 ways, then this 2 will also have 2 ways. This 2 basically says, hey, 2 is remaining from this 3 when 1 is being left out, 2 is remaining. This 2 says from 4 when 2 is coming out for the first, then 2 is remaining. But both the 2 mean the same thing. The 2 are remaining, how many ways can you give me for these 2 that are remaining? So the answer is bound to be the same. So somewhere, this part and this part we are redoing. We are having a redundancy. And that is what dynamic programming helps us in solving. Dynamic programming says, okay, if you have got, dynamic programming says that if you have got an optimal substructure where a problem can be solved by solving the subproblems, then look if you have some repeated subproblems. Here you have repeated subproblems or something that are known as overlapping subproblems. Overlapping subproblems. If these two conditions are satisfied in any approach, in any problem, that is where DP becomes applicable. If a problem or the structure of a problem or the structure of the solution or their subproblems satisfies an optimal substructure and overlapping subproblems, then it classifies as a DP, otherwise not. And that is what we are going to always observe. That can we express a problem in terms of subproblems? Can we express the overlapping things of a subproblem? For example, if this is overlapping, I can say, okay, first time you calculate it, next time don't calculate it. Store it somewhere. For 2, store it. That whenever 2 is going to come, the answer is going to be 2. Whenever 2 is going to become, the answer is going to be 2. So you can always calculate. For this one also you can calculate that 2. So that is how we will be covering it. From the bottom to the top, the results will be returned. So from the top to the bottom, the computation is going. And from the bottom to the top, the results will be returned. We will see live coding of this. The results will be returned in this way. So if I break it, basically 4, 3, 2, 1, 0. You will have 1, 2, 3, 4 as the first dice, and then let's say these are there, 1, 2, 3, and then you have 2, 1, 0. Then from here you have 1, 2, 1, 2, and from this one you will have 0. Now you will go up to the extreme bottom, and then they will return value. 0 will say, okay, I have no other way to go. You have one way up to me. You have one way. So 1 gets the answer of 1. 1 will say, okay, I have only one way to go downwards. There is only one way there. So I'll return 1. This 1 returns 1. So 1 is going to return 1. Or we can say that the answer of 1 is equal to 1. We have computed it. 1 is returning 1. Here only we have computed that the answer of 1 is basically 1. Next, 2. 2 is going to basically call 0 as well. Now 0, answer 0, we know it is 0. You can also write that as a case. Answer 0 is equal to 0. And now this will straight away return 0. Next, this 2 is going to add these two things up. Sorry, answer 0 is going to be 1. We discussed it. Answer 0 is 1, so it will be returning 1. And now we discussed that this one is going to give the sum of the ways. If it is going into 2 ways, okay, one way in the left, one way in the right, so add them up, 2 ways in total. So it's going to return 2. So answer 2 is equal to 2. Next, this 1, again, it need not call 0. This 1 can directly say, hey, I know for 1 the answer is 1. So it can directly return 1. 0 can also directly return 1. It will not go down. I mean, it anyway won't go down. Now the answer is 2 plus 1 plus 1, that is 3. Sorry, 4. So now it will return 4. And we will note it down that, okay, answer of 3 is equal to 4. Now, next time it comes to 2. For 2, we already know that the answer is 2. So we will directly return. For 2, we will directly return. This is like we are saving the computation. We will directly return what is stored there, that is 2. Then for 1, again, we will directly return that the answer is going to be 1. And for 0 also, we will directly return that the answer is 0. So at this 1, at this 2, at this 1, we are saving the computation. We are saving the computation by remembering. At these 3 positions, we are saving the computation, saving recomputation, by remembering the calculated values. And at the end, okay, 0 should return 1. I'm sorry for the mistake. Now if you add them up, so basically it's 4 plus 2 plus 1 plus 1, you will get 4 plus 2 plus 1 plus 1 is equal to 8. Okay, so we are getting the right answer. Now, one way is that you do in this recursive way, and whatever values you are getting, remember it in this way. Remember it somewhere and you can use it later. So this particular thing, remembering and using whenever needed, is known as memoization. So let's first code this recursion with memoization, and then we will see another technique of solving the same thing. So we basically have to take n different, okay, we have to just input n, that's it. So I will take n, yeah, and then I'll say, okay, few things missing, I'll add those things, import java.util.star, and then Scanner is C. For taking the inputs, I'm coding in Java. C++ code will be very much the same, less than I++. And then, sorry, we can actually call the different things. Yeah, so I can basically say that return me something like this, int, and this can be static. Okay, this has to be inside the class. Static int, number of combinations. Let's keep it something like this. We have the n over here, and we have the mod value, and we will call this, we can directly print this, system.out.println the number of combinations, n comma 10 to the power 9 plus 7, 1 2 3 4 5 6 7 8 9. Yeah, simple as that. And now I'll do some basic things, that okay, I'll do some basic recursion, that hey, if n is equal to this basic recursion, and then I'll do the memoization and show you what is the difference. So if my n is equal to 0, that is my base case, then basically return 1. There is only one way in that case. Otherwise we will say, okay, for int I equals to 1, I less than equal to 6, I plus plus, and I can say int y equals to 0. This is the sum, or I can name it sum as well. This is a number of ways, total number of ways I'm going to store over here. So sum plus equals to number of comb. I'll say that okay, do it for n minus I, and here something is necessary, that if I is greater than n, then break. We could have done this in a different way as well, but I'm doing it this way. If it is greater than n, then break. And here we are calculating the sum modulo equals to mod, yeah, and I'll return sum. This should give the correct answer. I'll run it once. For I equals to n equals to 3, I should get 4. So let's see that. Yes, I'm getting 4. But if I submit it, this basic recursion, why do we need a better code? We will understand that, but this is a basic recursion code. Now if I submit this, what is going to happen? Let's see, submit. Start Java programs. Yeah, there you go. Okay, Java, I've submitted. Now let's see. Time limit exceeded. This is the interesting thing. This is why you need to write optimized code. There are some test cases which have run in 0.1 seconds, but then there are these things which are having time limit exceeded. These are exceeding time limits. It's a small code. We will write the same code now with that extra factor that you saw over here. This extra factor, this memoization. I will just remember the values, and let us see what benefit that gives us. I'll just remember the values. I'll say, okay, please create some vector or some list kind of thing is equal to new int n plus 1. N goes up to 10 to the power 6, so we can afford this space. So I will just say, okay, answer 0 is 0. I'll maybe fill the things, arrays.fill. I'm hoping this works. Answer with -1. So answer 0 equals to 1. Okay, it's never supposed to be 0, so we can use 0 as well as the indicator. So I'll basically say if it is 0, that means it has not yet been calculated. So answer 0 equals to 1, and now I'll send the answer somehow. I will add a new variable there, that hey, these are your states, int answer. So here also I'll pass that answer. Okay. Now the thing is, when I come over here, I don't need this. I can basically say that, okay, instead of this, I'll just directly see, hey, if answer of n is greater than 0, then please return answer n. Otherwise, return sum. Before you do return sum, you can do answer 0 is equal, sorry, answer n is equal to sum. And then return that sum. So answer n greater than 0 basically means we'll directly return it, otherwise we will store it and then return it. What does this mean? That the next time the same value is going to come, I will exploit this line. I will return the answer n directly from the memory. So I'm remembering the memory what I'm storing, and I'm storing only n different values. So only n times I'm computing, other times I'm not computing. So let us see, if I do this change, then am I able to pass the test cases? Dice combinations Java, submit. Okay, now a few ones are giving time limit exceeded. That is interesting. Uh, we are not consuming much space, but okay, let us see. Number of combinations, this at the end only it should be calculated. I greater than n break, return answer n, return answer n. Okay, so the entire value, this answer n can actually be like some big value modulus 10 to the power 9 plus 7, and that can become a 0 actually. So instead of doing this, one other way is actually let it be a long. Long basically means you don't have to do the modulus operation always. That will save few things. So return long, pass long. That will save few things. You don't have to do modulus at all. You don't have to pass this modulus at all. This thing basically you can do it separately uh, over here as modulus 10 to the power 9 plus 7. Int long, this should be valid, okay, comma. Cool. What next? This looks fine, this will save some time. And this is more reliable. We'll be, yeah, we'll be avoiding more cases in that way. So yeah, correctness need not be checked. Let us now submit this. Okay, the more time limit exceeded. Answer 0 is 1. I equals to 0, I less than equal to 6, I plus plus. That should be fine. So it is okay. Now the only thing in my mind is scanner is a bit slow. So maybe we should try other ways. Or the other thing is, by the way, we can check what is the wrong answer. 50 correct answer is this. The user output is this. 10 to the power 9 plus 7. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 to the power 9 plus 7. N minus I I greater than n, we will not do the n minus i's things. Answer n equals to sum. Okay, sorry, this should be long. This has to be long. Now if I do, at least that problem is solved, but I mean the wrong answers will not happen, but the time limit exceeded are different things which need to be solved. Okay, so now you have some time limit exceededs. If I look at them, you have only 1000, for which if I have to say, hey, how much time are we taking, basically I'll put something here that system.out.println system.current time millis, that is what is a millisecond now, and I'll do this after this input as well. Actually, that's not fair. uh, we should do it after the input only, because we can't give the input so quickly. So there you go. I'll see how much time is taken by this, how much time in milliseconds is taken by this. Okay, so it's 68284. Looks like it is taking some milliseconds only for this part of the operation. If I do 1000, let's say I do it for 1000. Okay, it is taking some time. It is taking some time, which should not happen. Which should not happen. So I can do one thing. I can basically say, I can pass this over here, and I can say at the end basically do the modulus int mod, and over here also I'll pass the mod, and I'll do the mod at the end is equal to sum modulus mod, and I'll return this sum. Then I don't have to do this modulus thing later, and now I'll check it. But it should not have taken so much time. Yeah, now it is fine. So probably modulus was taking a long time or whatever, but now it should be fine. Yeah, so now it should be pretty fast. Okay, sum modulus mod. Looks like we are doing the modulus rightly now. For 1000, this is the answer, 937196411. What are we getting? We are getting something different, and we are getting something far bigger than the range. So maybe we are missing the modulus. So just in case that is happening, I'll do this. One modulus should not matter. Yeah. Now it is correct. So where are we missing that? Sum modulus mod, we are doing it here. Break means we are coming out here. Answer and we are returning here. Ideally that should not have happened, because I'm doing this. Okay, I'm returning sum. My goodness, that is a mistake. So instead of sum, I should basically return answer n. And over here, I should not do modulus this. This is now not needed. I'm returning the wrong thing. So I'm doing the modulus and I was returning the wrong thing. So yeah, now it should be fine. Yeah, now we can submit it. Dice combinations.java. Now few test cases are actually failing, but I think it's related to Java now. Let me see. Okay, there is an exception. Okay. That is interesting now. So for this, we have some tricks to actually prevent this that I've used at some places. So the thing for this is, the thing for this is I can increase the recursion stack. The thing is, if the recursion stack grows, then that becomes an overhead. Actually, this will leave some pressure on the system as well, because this actually demands large space. And this is where I think the next point can come. If you want to do it with less memory space, there is another way. So this one can be done, you can actually get, but now the issues are happening for the large memory sizes. So what happens is, if you're calling it for example, over here, see, you're calling it for 4. And what happens over here is, in your memory stack, 4 is calling 3, 3 is calling 2, 2 is calling 1, 1 is calling 0. However, if you do it for 10,000 or 1 lakh, something like that, if you do it for 10 to the power 6, that will call 10 to the power 6 minus 1, that will call 10 to the power 6 minus 2, dot 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 up to 1, which means it will call 10 to the power 6 number of times. And in the memory stack, in the recursion call stack, if it calls 10 to the power 6 number of times, that is very, very unoptimal. You should avoid it. And so, if you have less number of steps, for example, instead of 10 to the power 6, if you had something like 10 to the power 3, then this would actually work for all the test cases. More than time limit exceeded, this is actually memory limit exceeded kind of a thing. Your memory limit is getting exceeded. So there is another technique where we say, hey, don't call it recursively, calculate it in the sequence. So something like this, you know that 4 depends on 3, you know that 3 depends on 2, 2 depends on 1, and so on. So calculate in the reverse direction. If you have to calculate, let's say 6, start from 1, then calculate 2, then calculate 3, then calculate 4, then calculate 5, then calculate 6. So in this way, we will actually be able to solve it in a linear way without calling any function recursively. So logic remains the same. We are going to follow this particular technique only. The hack for making that pass is basically increase the recursion stack, but I'm not going into that. That's a hack only. We can't call it even a workaround. But now, the right way for this is a new technique known as tabulation technique of implementing DP. So we have seen one technique, that is memoization, which has one problem, which is the stack overflow, or your memory limit gets exceeded. Your memory limit can get exceeded. There are other issues as well, but there is one more technique, tabulation, where we say fill the values from left to right. And that will basically solve your problem in a linear fashion. So let us see how. So we can say this answer 0 equal to 1, calculate from the left to the right. For int I equals to 1, I less than equal to n, I plus plus, and solve it. So basically, for int j equals to math.max I minus 5, comma 1, sorry, comma 0, basically I minus 6, right? Yeah, I minus 6, comma 0. So from I minus 6 to I minus 1, those values are important for you. For example, for 7, 1, 2, 3, 4, 5, 6, all those values are important. You can subtract 1, 2, 3, 4, 5, 6. So those values are important. I can actually take this loop from 1 to 6 as well. That is probably better. J less than equal to 6, j plus plus. And then I'll say that, okay, if j is less than, sorry, if j is greater than I, then break. Otherwise, I'll say answer of I plus equals to answer of I minus j. And then, of course, answer I modulus equals to 1, 2, 3, 4, 5, 6, 7, 8, 9. At the end, you will return answer. you don't have to return answer, you can, yeah, you have to print basically. So system dot out dot println the last value, that is answer n. So now you don't need any separate function. That function was working correctly, you all know that. Now this is the tabular method of basically doing the same thing. We are just adding the values from the previous cells to the next cell. I'll solve it. I'll run it. So for 4 we know that 8 is the answer. For 1000 also it's something like this. So yeah, now let's submit it. Now it is accepted. So you see, this was a bias kind of a thing. The memory limit actually was not prepared to face so many recursive calls, and that is why what we did is we shifted to the tabular method. This is known as the tabular method because you're basically just using an array and going in the right order. So again, to reiterate what I mentioned here, we calculated the answer for these values 0, 1, 2, 3, 4, 5, 6. I know that 6 depends on 5. I know that 5 depends on 4. Let's say n equal to 6. For this you are calculating. I know that 4 depends on 3. I know that 3 depends on 2. I know that 2 depends on 1. 1 depends on 0. 5 also depends on 3, 2, 1, all those things. So dependence is towards the left. So if I solve from left to right, can I say I am free of dependencies? Whatever I need, they are already solved. So 4 needs 0, 1, 2, 3. They are already there. So I can pick up those values. That is the point. So that is how tabulation basically helps. So in this session, basically we learned how dynamic programming can be used to look at a problem in a stepwise manner, to visualize the optimal substructure and overlapping subproblems, and then to optimize that overlapping part using memoization and tabulation. Using memoization, you saw many extra test cases actually passed the time limit. We faced some memory limit exceeded, which was a different thing due to the recursion stack. But they were passing the time limit. They were all passing the time limit, even for large values. If I show the previous code, yeah, this was the previous code. If I ask for the largest value, that is 10 to the power 6, you will see it will actually give me the output pretty quickly when I run it. This is just a compilation. Yeah. Now if I run it, 1, 2, 3, 4, 5, 6. Okay, it happens pretty quickly. Now it basically exceeds the space limit. That's the only problem. But if I do for 1000, it happens very quickly. Yeah. If I do for 5000, then also, yeah, it happens pretty quickly. If I do for 10,000, okay, it cannot bear it. If I do for 8000, okay, fine. So 5000, somewhere around that, it has the maximum retention limit. But the thing is that the time limit issue has been solved by this memoization. It solves pretty fast. If you do the same thing without that memoization steps, you will see that for 1000 it will not happen so quickly. So that is what we covered. We actually saw these two techniques, memoization and tabulation. Now you know which one is better, why it is better. But in some problems, actually implementing memoization is far better and it works. So over there we say yes, implement the memoization. Otherwise, tabulation definitely helps. And in memoization, there are certain tricks by which you can increase the stack size. I showed this. You can actually use this. I use this in my template. You can use this new thread, null, new main, and something like this. So inside this, so basically we are starting a new thread, and the run function will get executed for that thread. And for that thread, I am basically saying that use this as your upper limit for the stack size. So here we are actually overriding that hey, use this much as for your stack size, 2 to the power 30 bytes. Okay, Hope you got some interesting insights. The next problems we'll actually solve using the same thing. I'll implement the ideas which I actually used in this session. We'll go into the same depth. We will see how in different ways we can solve it. So in this session, you saw me live coding. You saw me gradually improving. I'm working on this platform myself after a long time. So I was unaware of certain things. Now sometimes we see the bias that C++ solutions are accepted and Java solutions are not accepted. If I see the same thing on this side, I will shift to C++. The reason behind C++ Java problem is because Java takes more time for the execution of the same logic than C++ takes. Sometimes online judges give the same time. So if I see that kind of a bias is affecting our results, then I will shift to C++. Otherwise, we will stick to Java. And let me know if you want this in the other languages as well. Like if you want it in C++, we can have all the other things in C++. But I hope you enjoyed the session. I hope you learned something from it. And looking forward to see you all in the next videos where we will be upskilling, we'll be solving more difficult problems or related problems. Till then, take care, keep coding, and see you in upcoming sessions. Thank you.